Hey students, we just talked about what determinism is. So now let's talk about how to achieve determinism in different designs that we may have. Okay, there are many methods that are commonly used to do this. One of the most familiar is the 3-2-1 strategy. And so it's where you touch something on 3 sides on its biggest surface, 2 on the next surface, and 1 on the surface following that. And so let's look at that for just a minute here on this block. And so on this block, I want to touch the largest surface of this workpiece with 3 locations. So what I'm going to do is take these small pins and I am going to put them, assuming that I can get them into 3 locations. That one is being difficult. This one is being difficult. Okay, those are really tight fits. So as you can see, I've put in 1, 2, 3 to locate the first surface. And when I put that on there, I have eliminated 3 degrees of freedom. And so it cannot move down in the Z direction anymore. And it can't rotate around X or Y anymore. All of those are taken out. So the things that it can do now are it can spin around the Z-axis, and it can translate in X, and it can translate in Y. Now, you'll note that it can also translate in the positive Z direction up towards the camera, but remember, we have an assumption that after we have put these locators in, we're going to come and we're going to put a clamp on here, or maybe a couple clamps on here to hold it down against the locators. Okay, so then we need to put something in the next direction. So if we just said that 3 points defines a plane and we want to position this plane here on the side, why do we not use 3 points on the side? If we want to position a plane, we would use 3 points, right? Well, the problem is if we're assuming that this base and this part are completely rigid, and we're assuming that they are not perfect surfaces, then if I were to come in and try to touch this in 3 locations on the side, either the part would not be able to touch these 3 locations, or it would not be able to touch these 3 locations, because the likelihood of me being able to get these 3 locations exactly perpendicular to these 3 is very small, and the likelihood of the back surface and the side of the part being exactly perpendicular is even smaller, and especially of the surface finish in the places where I'm going to touch it, that is the smallest of all. And so what we're going to do instead is we're going to touch it in 2 places on the second side. So I'm going to take these 2, hopefully. Okay, there's 1. Here is another. These are really good tight fits to get precision, so it takes a little bit to put them together. So you can see that this is put together. So how many degrees of freedom do I have now? I eliminated 3 the first time, and now I've eliminated translation in X, because remember I'm going to clamp it over here, and I've eliminated rotation around the Z-axis. And so now I've eliminated 5 degrees of freedom, and that means that I only have 1 degree of freedom left, and that is movement along Z. I'm sorry, along Y. Okay, so let's see. When I wanted to eliminate movement along a direction, I put in 2 pins. So what happens if I do that and I put in 2 more pins? Well, the problem is I've now over-constrained it, because what do these 2 pins do? If I moved the part off of these side locators and just thought about these locators on the end, I limited movement in Y and rotation around Z. But remember, I already eliminated rotation around Z over here. And so again, just like the first point, even though I'm locating a plane, if I were to make this, the likelihood of me being able to get the plane created by these contact points on these 2 dowels to be exactly perpendicular to these 2 contact points on these 2 dowels and these 3 locating surfaces down here, that is almost no possibility that I'm going to get them exactly perpendicular. And if I look at this, the ability to get this side of the part exactly perpendicular to this side of the part and the bottom side of the part, and to get the surface finish exactly flat, that's just not going to happen. So I have what's called over-constrained the part. I have removed this degree of freedom, this rotational degree of freedom, twice. And so in actuality, this will not be deterministic anymore, because either the part will line up with these 2, contact these 2 sides, and then contact one or the other of these pins, or the part will contact these 2 pins and then contact one or the other of these 2. But it can't contact all 4 at the same time because I've eliminated some on the bottom. And so I can take out a pin. Okay, so now I have 3 on the bottom, 2 on the side, and 1 on the edge. And remember, I eliminated 3 degrees of freedom, 2 degrees of freedom, 1 degree of freedom, so that's 6 degrees of freedom limited. Okay, that sounds great. Have I eliminated them in the best way possible? Well, it depends a little bit on what the forces are going to be on this part in the process that I'm doing. In one way, this is not the best, because I would like my locators to be as far apart from each other as possible. And the reason is this. See how easily the part rotates around these 2? It kind of uses these 2 as a hinge, and it can rotate off really easily. So it's not very stable. If instead I had put this dowel over here, then the moment from this contact point to where this dowel is applying force is much larger, and so it is generally a better place to put it. In fact, now these 2 kind of act as a hinge, and so sometimes I might want it to sort of be in the middle. Again, it just depends on how I'm going to load it. Okay, is that the only way that I can achieve determinism with this? No, certainly not. There are lots of other ways that I can achieve determinism. I'm going to pull all of these out, and I'm going to use this really big pin right here. And so if I put that really big pin in, this one's a little bit loose because it is a gauge tolerance, it's a different tolerance level. But we'll assume that this were really tight. So how many degrees of freedom have I eliminated here? Well, if the part is down on this surface, the only thing that I can do with it is rotate it around the locator. So I've eliminated 5 degrees of freedom. Remember, it can move up the locator, but I'm going to clamp it down against the bottom surface. And so with this plane and this cylinder, I've eliminated 5 degrees of freedom. Is it deterministic? No, not really. Because just like we talked about before, I don't really have any idea where this flat is touching this surface down here. How could I make it more deterministic? Well, I could put in a small pin, and then I know, oops, that was the wrong place to put that small pin. Let me put the small pin down there. So now I know where the part is being located on this plane. It's being located on that pin. And so now it will spin. Maybe that is a better solution, but it might not be. So this is a more deterministic solution because I have now eliminated 4 degrees of freedom with this pin. It can't translate in X or Y, and it can't rotate around X or Y. And then the little pin down here has limited the translation in Z, but it can still rotate around Z. Okay, that might be good, but notice that it's not very stable because I'm only supporting it on the bottom right here. And then I'm depending on this to provide moment support against the rotations around X or Y. So if I were machining over here and pressing down really hard, you can see that it lifts off that pretty easily. So it would take a monster clamp to hold it in place if I were going to do this. That's a place where determinism may ask for one solution, but in fact stability may ask for another. So what would I do in that case? Would I, there are several things I could do. I could over-constrain it. I could make it not be deterministic by putting in 3 points on this surface down here to make it so it sits down more evenly, but it would be way over-constrained by this cylinder. It might be that I could also take this cylinder, and if this cylinder just barely, let's see, let me do that again. If this cylinder just barely protruded into that hole, it would provide almost no limitation on the moments around X and Y. The only thing that it would do is limit translation in X and Y. And so if I had a little short cylinder here that just barely came into the bottom of the hole, it would no longer be over-constrained because I would have removed 3 degrees of freedom here, 2 more here, and the only one that I would have left would be the rotation around Z. Okay, so there are lots of options here and lots of things that I can do, and each of them contains some assumptions. How many degrees of freedom this removes, the pin in this big hole, depends a little bit about what the contact length is along the sides. It depends on how tight these two are together. If the cylinder were really small compared to the part, well, let's go to the end case, which is a little tiny cylinder. Then it would really only eliminate 1 degree of freedom, or maybe 2 if you said it couldn't rotate in this direction, though that would take a really strong clamp. But so just because you have a cylinder in a hole doesn't mean that it only does or that it automatically does 4 degrees of freedom. It depends on the situation. All right, let's go back and look at this. That would be a better view for right now. So we could do 3-2-1, or we could do the concentric and radial strategy. Let me show you one thing on that. If we had done this strategy, remember that we had this Z location left, or Z rotation left. If we put a pin right here, that's pretty hard to see. Let me go to the bigger shot. If we put the pin right here, then that would prevent that Z rotation. So for this one, we have the center here providing 4 degrees of freedom, or limiting 4 degrees of freedom. We have this pin, which eliminates 1 more, so that's 5. And then this rotation that's left, we just do by holding it out at the edge. That's called clocking, when you prevent the rotation around Z. And we're going to talk about clocking quite a bit because it's a very common last degree of freedom to remove, is this rotation about some axis and just putting a locator out there and stopping it. It's called clocking. All right, we're going to need that as we go forward. All right, so we can do a concentric and radial strategy. And if you look in the book, you know, they spend all this time on 3-2-1, they spend all this time on concentric and radial, but here's the thing. What we really need to do is we just need to eliminate the degrees of freedom. That's what we really care about. Some parts won't fit either of these strategies, so we just need to eliminate 6 degrees of freedom, and we need to eliminate those 6 degrees of freedom well. There are some challenges to that, right? If 3 degrees of freedom is so great, then why do chairs have either 4 or 5 legs? Well, if you've ridden a tricycle, you know the answer to that. Tricycles are really unstable. 3-legged stools are really unstable. So sometimes, even though 3 points of contact is the most deterministic, we have to back off of that and get more support. And there are some ways that we can do that, how we also maintain determinism, but still gain the support. And so we'll get to those as we go forward. So anyway, what we really need to do is worry about the degrees of freedom. And so on every project this quarter, we're going to look at the degrees of freedom. We're going to make sure that we eliminated all the degrees of freedom. And so here are some rules or guidelines or suggestions. And I say that they're suggestions because each case is a little bit different. But in general, you're locating points, where you are locating the part. They need to be solid and stable. You want them to be as far apart as possible, assuming that the part is pretty rigid. As the part is less rigid, then you may need to move them in some, and you have to also look at where is the force occurring on the part. No redundant locators. So when I put 2 on one edge and 2 on the other edge, that was too many locators. And so that was an over-constrained condition. And so we don't want redundant locators if we can help it. And when we are sizing these locators and doing positions on them, remember that we are shooting for a tolerance on those positions that is 20 to 50% of the tightest part tolerance. And so these become fairly expensive parts, and the location that the thing that's holding all of these with such a tight tolerance becomes a fairly expensive piece as well, because we're working in really small numbers here. And then finally, if possible, you want to locate it on mutually perpendicular planes. And the reason is because if I don't do it on mutually perpendicular planes and then I put my clamping force in, it will cause an additional force or moment up the non-orthogonal plane. And so mutually perpendicular planes whenever possible. Okay, so yeah, we'll talk about these briefly. As we look at these, we're going to talk about these a little bit more in class, but I want you to think about, are these deterministic? If I touch the sphere in 3 locations, do I know where the sphere is? Yeah. A sphere can be defined by 3 points. And in fact, we could figure out how many degrees of freedom does that remove, and we'll talk about that in class. A plane with 3 points underneath it. Yeah, that's pretty deterministic. What about this cylinder with 3 points? 2 on the sides and 1 underneath. Well, this is a quasi-static, and so you can see that the cylinder is balanced on this 1 point, and it is deterministic as long as it is in the stable point. But if it moves off to the side just a little bit, it can fall off that one single locator on that end. So it is quasi-deterministic. It's not a good practice, but it can be done. Okay, so 3-2-1, just talking about the 3-2-1 rule, or one way to approach things. Okay. Most parts, I will tell you, don't really work that well with the 3-2-1, probably because of stability. This is one example from your book, and this is probably the best example of 3-2-1 I've ever seen. The part is essentially triangular. I mean, it's got a rounded edge on here, but it's essentially a triangular part. And so when you fixture it in 3-2-1, you don't get very far outside the stability of the pin on the single end, no matter what you do. So this is a really great example of 3-2-1. I will tell you in real life that 3-2-1 does not work as well as that in general. Okay, so the last 2 concepts to cover are over and under constraint. So if we constrain a degree of freedom more than once, that's called over-constraint. And the part doesn't actually even have to be fully constrained to have over-constraint. So if I were to take this part, and I had already put 3 locating points underneath it, and then I put 2 more, here I'll put 2 more on the edge towards you. No, if I put 3 more on the edge towards you, even though the part is not constrained, because I haven't finished constraining it, it is still an over-constrained part in one way, and that's because I have over-constrained this 1 degree of freedom. So anytime you over-constrain one of the degrees of freedom, that is reducing determinism. However, it is often increasing stability. Okay, if we instead don't restrain all of the degrees of freedom or constrain them, then that is called under constraint. And so the question is, would we ever over constrain a part? Well, yeah, we do sometimes over constrain it, especially a flexible part. We will over constrain it because we need to hold it in a lot of locations. Would we ever under constrain a part? And the answer is, in very rare cases, when there are low forces involved and small likelihood of somebody getting hurt. But in general, never under constrain a part, because it can be very dangerous. The part can break loose and come flying off in the unconstrained direction. And so in general, we never under constrain a part. Occasionally in measurement, like with the coordinate measuring machine, we will under constrain the part, and the reason is because the very first thing that we do with the CMM probe is come in and touch all the edges to locate the part. But it is a slow method of doing things when we could have put correct location in place and then not had to find the planes before we started measuring the part. We would just know where the planes of contact were. All right, so we will, in the next video, talk about, well, let's see. Oh, I guess one last thing. Sorry, I said that before, but one last thing is that we want the parts to be, or the contact points to be far enough apart, because we don't want to have a situation like this where the cutting tool is causing a moment that is going to lift the part off of the locators if we can help it. And so we would rather have it so that the force of the cutting tool is interior, inside the locators, so that there is not this overturning moment. Now that's not always possible, and we could do the first condition there if we had enough clamping force around the part. And so it certainly can be done that way. We just have to be really careful about it, because if we have this overturning moment, it means that our clamping force has to be much, much higher than we were originally planning. Okay, great. I will see you for the next video when we talk about the types of locators, because we don't always just use little pieces of dowel pin that have been cut up. All right, thanks.